a little bit earlier. Okay, so Parag really set us up for this this last topic. He mentioned two things that we're going to follow up on. The first thing is that we are often interested in also the allocative effects of various assignments. And so how should we think about that? And he mentioned three different applications. He mentioned schooling, where you might care about whether students are going to schools that they are well matched to in terms of what their downstream educational outcomes are, perhaps test scores or even longer run incomes. And he also mentioned public housing. Dan talked about the public housing allocation system, and he referenced a paper by Winnie Van Dyke that does something similar. And then he mentioned organ allocation. So I'm going to talk about the first and the third, and I'll be building a lot on stuff that Parag has done in this. And the second thing is thinking about this point that Catherine brought up about, do students value the schools that do they value and do they express demand for the schools that have good outcomes? Okay, so we're going to try to take those two things on. And so I think this is a sort of an important type of discussion to have for two reasons. So we've spent a lot of time thinking about utilitarian notions of welfare or Pareto efficiency type of notions. And they're basically based on the choices that people express. And so the notions of efficiency that Irene mentioned are based on whether students are assigned to schools they like more. Okay, but if you discuss this, school reform with a policymaker, I'm sure Parag will agree with this. They will often care about what is the educational attainment of the students, particularly, both in terms of overall achievement as well as whether the distributional effects. Are we serving all populations, all socioeconomic strata well in the assignment process? And that's an important thing to consider. Public housing, for similar reasons, you'd care about socioeconomic outcomes, you'd care about mobility. There are these important experiments, moving to opportunity experiments, that focuses on that. And then in organ allocation systems, we can talk about this notion that I mentioned about equivalent life years or whatever. And then, what the organ allocation committees are going to often look at is life years from transplantation. So let's take a patient who's on the kidney waiting list. Let's consider what's the half-life of this patient without a transplant, and what would be the half-life of the patient with a transplant. And the difference between the two is maybe life years from transplantation. And that's what they would often focus on. Okay. And so what we want to make sure of is that, these systems not only do well on giving people what they want, but also potentially are helping people out on these dimensions, because those are important outcomes to consider. Okay. And there's a question about whether the choices that people make is aligned with matching people to the right types of options for them, so that these outcomes are maximized. And there's you should sort of not take that for granted for a second. Okay? You might think that, if you give people the choice to pick whatever they want, maybe they will pick the right ones, maybe they won't. What are some reasons why choice-based mechanism may not end up resulting in an allocation that does really well on also improving these outcomes? What are some reasons that might occur? Any ideas? Yep.
In school choice, if there's imperfect information, students might undermatch or overmatch, go to schools where they ultimately drop.
You may not know which schools are the right ones for you. You may not know which schools are good, right? And so you may not express that kind of choice. So that's one reason why that might not happen. Any other reasons? Yes?
Taking into account externalities.
Okay, elaborate on that, please. Could you elaborate a bit more?
The social benefit of education, in particular, or productivity.
Yeah, so suppose I apply and I apply to a really good school, and I end up taking a seat at that school. That means somebody else did not get that school seat, right? And it isn't to be taken for granted that my match quality for that school was higher than your potential match quality for that school. Okay, so these 8 people are interacting in these systems and everybody's expressing choices, and there's no theoretical reason that the equilibrium outcomes are going to be such that when this interaction plays out, that people are going to be matched with schools that are going to end up resulting in better outcomes for them. Okay, and so what we're going to try to do today is to take the next step from using the data from these assignment mechanisms for estimating the allocative effects, the effects of these assignments on downstream outcomes, and thinking about what that implies for the kinds of assignments that we see and how people are matched. Okay, a second reason in the school choice context that people care about whether people express demand, whether students express demand for schools that are high quality, is that the original motivation for, one of the original motivations for school choice was that when students and parents express demand for high quality schools, if they understand that and they express this demand, then perhaps that creates incentives for school systems, for the school principals themselves, to invest in improving their schools, and choice becomes a conduit for providing those incentives. So we'll address and analyze those questions. Okay, so what I'm going to try to do is to try to give you a broad strokes framework first, under which you can start thinking about these kinds of questions. Okay, it's going to simplify certain things relative to the specific papers. I'll go to a very simple example with one school, and there's a lottery, a charter lottery. This example is taken a slightly more simplified version of Chris Walter's job market paper that Parag mentioned, to give you a sense of what you get with sort of an offer instrument versus something else that you might be interested in, and how demand might be correlated or not with school quality. And then I will discuss a paper of Parag's with Chris Walters, Atul Abdul Qadir, and John Schellenberg that does this with many schools. Okay, always risky to talk about your advisor's paper while he's in the audience, but I'll do that nonetheless. And then we'll discuss the kidney allocation problem, and then I'll conclude with some broader thoughts. Okay, great. So here's some notation. So imagine that you have objects that are indexed by J, and you have students that are indexed by I. So that follows exactly what I did in the previous lectures. And then now in the previous lectures, we had the values of the agents for each of the objects. This should be a V1. And we had a vector evaluation. So Paulo's lecture had the value of the outside option, which is not remaining assigned. And then you had the value for school 1 all the way to school J. Okay, these are your random utility terms. Okay, and Parag's lecture had these potential outcomes, these Ys. Okay, so you have Y0, Y1 all the way through Yj, which is what would be the educational attainment of student I if they were to go to school J. Okay, and they might be different. You don't observe all of them, you only observe that for the school that they were assigned to. In all of these mechanisms, what really happens is that as a function of your valuations, you take some action. Let's call that action D. So there's some action D of V, right? It could be submitting a rank order list, for example. It could be applying to charter school. It could be in the kidney system, which kidneys you accept and which kidneys you decline. Okay, and so the decisions that you observe will have some information about V. They don't directly have any information about Y. You see then an assignment, because you have this administrative data. That's one of the things that we love about these systems, that you get a rich source of data and opportunities for empirical research. So there's an assignment TI which says, you know, which one of these J options was unit I assigned to. Okay, so it's either 0, 1 with the restriction that that each agent is assigned to only one option. Okay, so what you have data on is the outcome for the assignment that you saw. So if you had data on the kidney allocation system, and you saw that patient I was assigned to kidney J, you would see how long this patient lived with that kidney, but you wouldn't see how long this patient would have lived with another kidney. Okay. You see which kidney they were assigned to. So this is TI is a vector of dimension J with entry 0, 1. You see some of the decisions, and you see some covariates Xi of the agents. Right. And if you think about this model, there's a lot of potential for selection into assignment. Okay. There's potential for selection because some people who sort of benefit from any assignment. So people who benefit from any kidney, no matter which kidney it is, could be more likely to be transplanted versus patients who don't. Or it could be that students who are assigned to some school, some charter school, are more likely to benefit from charter schools than who are not. People could be assigned to specific schools that are better on average. So the value added of J, which is sort of the average benefits of assignment across all I given to J relative to the assignment, relative to the expectation for that particular individual. And there could be also the potential for match-specific gains, that if I'm assigned to J, then my benefits from J are higher relative to my expectation unconditional on being assigned. Right? And so, there's a lot of work on these types of models. Roy selection models is one of the sort of things that we kind of think about. It's kind of called Roy selection, where you say that, okay, your valuations and your actions are going to potentially select you into various kinds of assignment. Okay, so how do we try to make progress on this? Okay, and so there are two types essentially of things that the literature uses at a broad strokes level. The details are definitely there are lots of richness within each single type, but in broad strokes, there are two types of strategies that people use. The first type of strategy is the type of strategy that Parag explained in the previous section. What you want to do is you want to extract some randomness in the assignment given the preferences. You could do this in a relatively naive way, but now there are more sophisticated ways that Parag talked about. Okay, and roughly what's going on in that is that what you've got is these potential outcomes of these vectors. This vector of potential outcomes is independent of your assignment, controlling for covariates and your VI, which is your valuation, right? So that's you've got this conditional independence assumption, and what Parag at a high level explained is instead of having to control for extremely high dimensional version of VI and XI, what is a sufficient control for this based on the propensity score that is significantly lower dimension, so that I can pool people more cleverly in order to make progress with this conditional independence assumption, which full type conditioning would make life much harder. And so here that is sort of at a high level what you were doing, right? Is that's a fair characterization? Yeah. Okay. And so why might there be some randomness in the assignment? One type of randomness in what I get happens because in a small economy, not in a large economy, but in a small economy, it's possible that what else my peers are ranking and what they're demanding, which is put random from my perspective, could create randomness in my assignment. So that this would happen. Imagine that there are like 5 or 6 students that are competing for a small number of school seats. Who else I happen to be matched with in that particular year in terms of my competition could affect who I'm getting into, right? In a large market, that type of randomness does not happen because you aggregate across all the distribution of preferences of the population. The second one is that there's a lottery or tiebreaker in the mechanism, and then you combine that with information that you've got about sort of in the large market limit, what the cutoffs are going to be, and you use that to try and extract the right kind of juice from the assignment system. Okay, and here, if you think about this in the previous lecture, what we did was we took detailed knowledge of how exactly the mechanism works and use that to figure out what is a sufficient set of conditioning variables by using the mechanism. Okay. A second type of thing which is used more in this literature that I'm going to discuss is an exclusion restriction. Okay, so for example, let's say that the distribution of the potential outcomes for two individuals who have the same valuation but different x's. So if your xi is x versus your xi is x prime, okay, if you can make the assumption and you can justify the assumption that the distribution of potential outcomes is the same for the two, then you can use that to potentially shift the assignment because of the x's and make progress. Okay, and I'll give you a concrete example of how that works. In the one lottery case, one school, one lottery case, but as a preview, it's sort of like distance. Maybe the distance to the school, distance to various schools affects whether or not you want to go to that school. And we're going to potentially exclude that from yi and make progress that way. So let's see that in operation in the one school lottery example that is simplified from this nice paper by Chris Walters in 2018. Okay, and the question in that paper is whether parents demand effective charter schools. Okay, and so for in the setting that Chris is looking at, you have to apply to a charter school, and once you apply to a charter school, then the entire pool of applicants who are if the charter school is oversubscribed, then the pool of applicants that apply to it are going to be, and the selected subset from that pool is going to be taken from a lottery. Okay, so you win a lottery. If your lottery number is high, then you end up getting into that charter school. And I think there's a movie called Lottery, the lottery that discusses this process and the stress related to this process. That's worth a watch. Okay, so there are two types of things that are happening right now. So if you think about an agent in this economy, first you've got to apply. The ones that apply are expressing some kind of preferences, which may be correlated with their value for the school and maybe correlated with their benefits from going to charter school. The second is that conditional on applying, conditional on a set of applicants, a subset are randomly chosen by the lottery. Okay? That latter step creates random assignment that you can compare the people who won the lottery relative to not. Okay. And you can get some treatment effect, the effect of winning the lottery, right? And then you still are going to be left with that first step of selection into the application process. Okay. Now this is simplified from Chris's setup, because in Chris's setup, there's another stage called the enrollment stage. So once you win the lottery, you still have to enroll. Okay, and so that creates another layer, but I'm simplifying it because the main ideas can be explained with this somewhat simpler example. Okay, so let's imagine that we take a student, I, who is assigned to a charter school. So what is that given by? First, the student has to apply. So there's an indicator AI, which has to be 1. And that is 1 if VI minus XI, let's say, to simplify things, is positive. XI, let's think of XI, sorry, the subscripts 1 are typos, but XI is the distance to, let's say, the closest charter school. And because it's one charter school example, there's only one charter school to think about. So there's your random utility component minus the XI, the distribution of this random utility component, unobservable, other observables and unobservables. It can be fully non-parametric, but it has this additive form. Okay, and so students that are further away from the charter school are less likely to apply. And then you've got the ZI, which is an indicator for whether or not you won the lottery. Okay, so if you won the lottery and you applied, you get into the school. So there are important simplifications here. So there's no enrollment stage in this model. In Chris's model, there is one. In Chris's model, there are many charter schools. And so there's a portfolio choice of applying to a set of charter schools. And there are no other covariates. So he has a demand system, et cetera, with many options, et cetera. And So I'm simplifying things, okay? And if you look at this model, it's basically Heckman and Navarro 2007. Okay, that's why it's useful to go to the simplest case, right? So now let's assume that your distance to the charter school is independent of your VI, which is the random utility component, and the potential outcomes of going to charter versus not. Okay. And so you'd go to a traditional public school if you were not assigned, if you did not enroll in charter school. And then offers are randomly assigned, and it's random of everything else. It's independent of everything else. This particular assumption can be verified because you know that a lottery is what is generated. Okay. So now, given the second assumption, if you estimated an IV model, the estimate of the IV model would be the following. It would allow you to look at the applicants of charter school, right? And here I'm making the assumption that if you apply to the charter school and you get the lottery, you would enroll. So there's no enrollment stage. Enrollment is perfect compliance, right? Just to make things simple. You look at the applicants who won the lottery relative to who did not win the lottery, and you get the treatment effect of individuals who applied to charter. And so the VI must be bigger than XI. Okay. Using the first assumption, this distance covariate, what Chris does is to extrapolate to the unconditional or the average treatment effect. Okay, so it's it says that, okay, let's think about people who are so close to the charter school that they apply for sure, for example. Okay, and so for those individuals, no matter what their VI is, they're going to apply, right? I told you that distance to charter school is not correlated at all. It's independent of all these potential outcomes. And so using that subset of individuals, you get the average treatment effect. Okay. And so the average treatment effect could be different from the IV estimate, because the IV estimate is the treatment effect for individuals who applied. And so there's implicit selection in that application stage. Okay. And using this identification and infinity argument, which should be familiar from the Heckman selection model, you can get this unconditional estimate, which is the average treatment effect. The comparison between these two tell you whether or not those that apply to charter school are ones who are selected to benefit from charter schools or not. Okay. Is this one school's very simple example clear? Because we're going to put this on steroids soon. Okay. Good. So I'm going to leave the bottom line of that paper as suspense for you guys to take a look. Now let's go to the school choice case where there are many schools, and we'll discuss Parag's paper with Attila Abdul Qadir, Schallenberg, and Walters. Okay. So the question in this paper is whether the demand for high value-added schools is higher. Okay. And as Parag mentioned, and I also reiterated, this idea is important. The answer to this question is important because it partly was a big motivation for school choice. So the idea is that students will go to the schools that are high value added. The low value added schools might be undersubscribed. Few students may be there. And so we'll potentially be able to push principals to either increase investment in improving quality or maybe find out which schools should be shut down based on express demand, if demand is very correlated value added. But if it's not, then this channel may not function really well. Okay, and there's a lot of work in the labor literature that goes into this. And if demand is not correlated value added, it creates all kinds of incentives. It creates incentives for schools to potentially cream skim and find the students who are going to benefit the most. Who cream skim the best students as opposed to invest in quality. Okay. So in this paper, Parag and his co-authors are going to use application outcome data from the New York City high school match, which you heard about yesterday, from 2004 to 2007. And as a reminder, this system uses a variant of the deferred acceptance algorithm. And so what we see is a rank order list of schools that each student applies to. And we can see whether there's detailed data on where the students live, where the schools are located. You can compute the distance to various schools. You can look at their rank order list. You have the characteristics of many of these students. And you've got data on these rank order lists merged with downstream data on test scores at time of during high school, graduation rates, and they also merged it in with college attendance information. And so the main goal of this paper is to estimate the demand and school value added accounting for this type of selection that we explained in a very simple one school example. Okay. And what the paper is going to try to do is to try to understand whether this demand is explained by the quality of the peers of the peers that the students expect to have in these schools, or the value added of these schools. Okay. The approach in this paper is to first estimate a random utility model of school demand. We learned how to do that yesterday. And then using estimates from this demand system, they're going to control for the selection into the schools by using the rank order lists of the students and their characteristics. Okay. And then finally, they will take those selection corrected value added estimates and see whether demand is explained more by the selection corrected value added estimates or by the composition of peers in the school. So how is this done? So first, there's an outcome equation which says that the downstream outcomes, say test scores, graduation, or college attendance of student I at school J is given by this form, linear form. There's alpha J, which is what you might call the school quality. Then there's Xi times beta J. So that creates some observable dimensions of match quality between the student and the school. And then there's a shock epsilon ij. And in order to interpret alpha J as school quality, we're going to normalize, we're going to demean Xi, and we're going to demean epsilon ij. Okay. And what you observe in the data is only the graduation outcome or the test score outcome for the school that the student went to. They're going to take a logit-like demand model. There's going to be bins of students based on their observed characteristics. And there'll be a mean utility for each school that depends on these bins of characteristics. That's the delta sub C of Xi comma J term. Okay. And then there's distance that is multiplied by a covariate specific by the same bins, which has a coefficient that is student bin specific. And then there's you have your eta ij term that is type 1 extreme value with a normalized variance. Okay, like in the other paper on New York City, we're going to assume that rank order lists are truthfully reported. Okay, and this assumption, as we mentioned yesterday, is motivated by the idea that deferred acceptance with unrestricted lists gives you incentives to reveal your true preferences. Okay, and there's some just like in the other papers, there's a lot of work to sort of validate the robustness of the results to alternative assumptions, like just using the first few choices, etc. Okay. Of course, with deferred acceptance, with the restricted list, you have to worry a little bit about the potential for strategizing. Okay, but New York City gives you this recommendation that you shouldn't. Okay, so in this paper, why would there be selection into schools? Selection into schools would be captured by the correlation between epsilon ij and eta ij. Okay. So if it is the case that your preferences for a particular school are stronger if the yij that you expect from the school are stronger, then eta ij and epsilon ij are going to be positively correlated with each other. Okay, and so if you ran a standard regression, a standard value-added model, in which you took the yij's, the yi that you observed, and ran a regression like the one above, you could get potentially biased results, right? Because the value-added model makes the assumption that there's only selection in observables. So specifically, the expectation of yij, conditional on the covariates and the assignment ti in the standard value-added model is just alpha j plus xi times beta. Okay. The approach that this paper takes is to posit a different model in which, although they work with both models, to posit a different model in which they're going to control for the selection using the rank order list data. Okay. So specifically, what the paper is going to assume is the following form: that the expectation of yi conditional on treatment, conditional on assignment into j, the vector of distances of all the schools from student i's residence, and the eta I terms, the vector of all of the eta I terms that enters the random utility model, is the same thing as above, but also has this other term, g sub j of the vector of distances plus the vector eta I. Okay, so the main assumption here is that there is an additive separability in this in the functional form that relates the selection on eta and distance from the remaining pieces. So it's not a random coefficients model, for example. Okay, and so effectively, it's assuming that conditional on the rank order list, that the students, or the conditional on their preferences, the assign and their distance, the assignment is random. Okay, there's no residual selection. Okay, and so reasons why that might occur is that in the New York City assignment mechanism, there's tiebreakers, there's the reports of the other students, etc., and all these things are going to be sources of assignment that's going to place different students into different schools, and they're assumed to be orthogonal from yij, from the potential outcomes. Okay. Now this function gj is j specific, so it allows for the effect of distance to differ based on the school's identity as well as the distance to that school. So it allows for fairly rich correlations right here. Okay. Now, in principle, that particular control function, or the control variable, is quite high dimensional. Okay. So to operationalize this selection correction, what Parag and his co-authors are going to do is that they're going to parameterize this function g somewhat more restrictively. They're going to take the term from before, then they'll take the vector of distances to each school multiplied by a vector gamma, and plus there's going to be these two terms. The first term says that if individual I likes school k relative to the mean of eta, that those types of students might have, in general, higher achievement from any school, perhaps. Okay, or different levels of achievement in any school, perhaps. That is with that is multiplied by this psi k term. So those who like school k particularly like school k, may be better students, for example. Okay, just liking that school might be indication of that. And then there may be a match specific value. Var phi times eta ij minus mu eta tells you that if you like this particular school, perhaps you like it because it has higher value added for that school. You have higher value added for that school. Okay, and this type of control function follows the Dubin and McFadden logic as well. So now let's take this, this expression, which conditions on eta I. Now remember, what the students report is not their cardinal preferences for every school. They report a rank order list. Okay, so you don't know any student's eta. What you know for each student is their rank order list, their distance, and their characteristics. So now let's go ahead and replace the conditioning on these terms by just the conditioning on the rank order list and distance. Okay, and once you do that, you'll take the expectation of this term and this second term here, the eta ik minus mu eta, and the eta ij minus mu eta term, and those conditional expectations will be a function of only the conditioning variables on the left-hand side. Okay, and so let's define this function lambda sub k as a function of the characteristics, the distance, and the rank order list, and that's what gets substituted if you look at this particular conditional expectation. All right. Let's think about this expression here on the right-hand side of this equation. Let's say I've estimated my demand model, my logit demand model. Okay. This conditional expectation can then be either simulated or, in the logit case, derived in closed form. Why? Because the rank order list tells you a particular selection of these etas. It's like the cones that Paulo showed you. Okay, the cones look a little bit simpler because it's deferred acceptance, but it's the conditional expectations of eta given those kinds of cones. Okay, and so you can compute that. Once you've computed that in the first step, you can plug it into this regression. And what you've got is selection corrected estimates of alpha and of xi times beta j. Everybody with me? Parag, would you like to add anything to the?
Sorry, yeah, that's great.
Okay, so you get these estimates, and just like in any other estimates of value added, what you've got is a lot of fixed effects. You've got these alpha j terms, that's one for every school. And what you want to do is you're concerned, slightly concerned at least, that the variability in the alpha estimates also reflects sample noise. Okay, and so what you do is you want to use a Bayesian shrinkage estimator to reduce that sample noise. Okay. Now, if you're concerned about this, you don't necessarily get the value added, an unbiased estimate, the consistent estimate of the value added for every single school, but you get the distribution right. Okay, depending on however you want to interpret this. So depending on whether you have a long enough panel, if you have a long enough panel, you might say that, okay, these are also consistent estimates for every single school, but you definitely get the distribution right, and you get something that is unbiased. So here's a plot of the value added estimates without doing this control function selection approach and using it, right? So on the horizontal axis, you've got a standard value added estimate in which you've assumed selection only on observables, and the control function estimates that correct for this step where the demand that you have for the school might be correlated with your benefits from going to school. Okay.
So the data is a time series of a lot of schools.
So there are lots of students that are going to these schools, right? And if you have many students, and they also have 8-9 years of data. So if you have a lot of data per school, then you might think that the estimates for every school is pretty precise.
So the panel dimension of students, different students.
Yeah, you can think of the panel dimension of students, right? Across the various years schooled in. And then you've got these control function corrected estimates. They don't line up perfectly, although they are very highly correlated. Okay, so the selection correction is doing something. And this is for math scores. And so they do this for a number of different, 5 or 6 different outcomes. Okay. For college attendance, so this was the one which lined up the most. And this is the one that lined up the least. right? So if you looked at college attendance, the value-added estimates would suggest that there's a lot of dispersion across schools in their value-added estimates. So the horizontal axis is the standard deviation units, okay, of value-added of college attendance, right? And so you can see that there's a huge dispersion in the baseline selection on observables model where you don't correct for these the control function. When you do the control function correction, you see that there's a lot less dispersion across schools in the quality of various schools in their effect on college attendance. Okay, so this control function selection correction is doing something. Okay, and what this is saying, the fact that these estimates are quite different, is saying that maybe a lot of what we see in terms of the dispersion in the standard value-added estimates is coming because of the students being selected into or selecting based on their preferences into various schools rather than these schools affecting whether they go to colleges, whether they go to college or not. It's more that it's a student-specific thing. Yeah.
Is there some way to sort of test for how well the control function estimates or any sort of various methods of correcting for selection or accounting for selection goes versus sort of just looking at with or without and doing something sort of like that?
Yeah. So one thing that you might want to do, and I don't know if a paper that does this. I mean, there are some papers that have compared value-added estimates from estimates that are obtained from random assignment. So that's one kind of exercise that you could do. You have to be a bit careful because depending on the source of the experiment that you're looking at in the random assignment, the estimand might be a bit different because one might be estimating a late and the other one is targeting an average treatment effect. So you have to be a little bit careful about doing that kind of comparison, but that's the type of comparison that you'd want to do. Anything else?
Yeah, that's right. We actually do some of that in this paper, but because this is disaggregated to the single school, the lottery estimates are really noisy, so those tests tend to be pretty underpowered. Just another point to add, I think this literature feels fairly comfortable with selection on observables for test score outcomes because there's a lag in the score, like your baseline scores. But if you try to look at outcomes that don't have a lag, like college or graduation, people feel much less comfortable. So that's why
And there's a series of papers by Peter Hull and co-authors. What they do is they get value-added estimates and estimates from some experiment for various schools, and they regress one on the other and see whether you get a coefficient of 1 to see whether to validate essentially these types of estimates. So that's the kind of comparison that people usually do. I'm not an expert in this literature, so help us appreciate it. Okay, good. So here's a table that shows the correlation between your pure quality and the average treatment effect based on the control function approach estimates. Okay. Why? So one reason why I'm putting this table up is that this table will be informative about how good a proxy are the kinds of students going into a particular school for the value of going to that school. Okay, and so you can see that the average treatment effect estimates are correlated, in some cases quite strongly correlated, with certain measures of peer quality. They're not perfectly correlated with the measures of peer quality, but somewhat correlated with the measures of peer quality. So to some extent, parents might be using peer quality as could potentially use peer quality as a proxy for value added in the demand system. You'll see exactly how peer quality is correlated with it and how closely demand is correlated and what explains how much of the demand patterns in a few slides. Okay, so the next step of the exercise is to take the estimates of demand. So you have these fixed effects, which were student demographic cell specific, and regress them on a dummy for the cell. The estimated quality of peers, right, and the average treatment effect of as estimated from these value-added measures, and also this match-specific effect. So that was that expectation of that last term in that expression right here. So like the phi times the selection on the match-specific gains. Okay. And so this type of regression will tell you something about whether the students, if say, for example, if rho 2 is positive, that means that students express demand for schools with high value added. Or if rho 1 is positive, that indicates that students express demand for schools that have high quality peers, and so on. Yeah.
If I think about this like as a price elasticity,
yeah,
is this like instrument like enough, even if I assume that maybe the schools are like choosing their value added, or if I assume that supply response something is like not identified?
So my interpretation of the estimates on the paper are not to estimate the sort of quote unquote causal effect of what would happen to the demand of a school if you changed value added by a unit or you changed peer effects by a unit, but more trying to explain whether the demand is explained primarily, or trying to investigate whether demand is primarily explained by value added or primarily explained by peer quality. It's not doing the experiment of take a particular school and change the quality of the school by unit, see whether demand goes up or down. Is that fair? So for that reason, you wouldn't be so concerned about the potential endogeneity types of concerns. You can always estimate. It's always in the data. It's always true that the expectation of y conditional on x is identified if y is the outcome variable and x is the covariates. Now the interpretation of that that regression function, which is always identified, whether that's the interpretation you are interested in or not is a separate question. So they will be interested in the regression function itself, which is always identified. Okay. So here's a table. I'm going to focus on the control function models. In column 5, this is again for regions map to keep it parallel with the slide that I showed you earlier, in which you've got measure of peer quality and that regression above, and you see that peer quality comes in positively. In column 6, you see that if you regress demand on the average treatment effect, that comes up positively. Okay. So demand is correlated with both peer quality as well as this measure of value added, okay, or of school quality, sorry. In column 7, what they do is they put both of the covariates together. Once you put both of the covariates together, what you see is that the relationship between the the quality of a school and demand is almost entirely explained via the peer quality variable. So this coefficient is indistinguishable from 0. Okay? So that means that once you control for peer quality, then the quality of the school does not have additional explanatory power on demand. Okay? So if you thought that parents or students were using value added or quality of the school as in order to express their demand, well, you have to confront this fact. Are they focusing specifically on value added, or are they using some other proxy and they don't have as good an information about the quality of the school? Okay. And then finally, they put in the match effect, and the match effect, surprisingly, turns out to be somewhat negative. Okay.
Could it be that the parents can't distinguish either, but they just see these good students, there's good students and they have good outcomes. I want my kid to go there, right? And they don't know if it's peer quality or the effect, but they just see good stuff and good students.
So what's the difference between the good students and peer quality? I'm trying to in your.
Well, in other words, is it, is the school is having good outcomes? Is it because it's just drawing a lot of other good
Right.
students? And maybe the parents just don't care. They just see, these kids graduate and they go to Brandeis and they go on to MIT. So I want to send my kid to Brandeis.
That's exactly what this regression is showing. That peer quality is like, how well are the students doing on Regents math scores, and they're just essentially using potentially that as a proxy.
Yeah, so the parents don't necessarily have to make that distinction when they're right. In other words, are they able to make that distinction between what the school's value added and the peer quality?
And that the regression is showing that perhaps not. That conditional on the peer quality, they don't have additional information about the value added. Is that? Yeah. Okay, and so here's a bivariate relationship between the mean utility term and the peer quality versus the school quality as measured by the Regents math effect. Okay, you can see a positive slope on both. And then they have another paper another figure in the paper in which once you control for peer quality, the second picture, the relationship becomes slightly negative even. Okay. Any questions about that paper?
So if you think that in the hypothetical case, or not in this case, that the estimate of the ATE is very noisy.
Yeah.
And parents are very good at selecting themselves into schools with very high real ATE. So I'm thinking that there may be a correlation in data between actual ATE and peer quality, but then your estimate of ATE is noisy. So you have attenuation bias.
Yeah.
So that,
Yeah.
I don't know if
So Paulo's question is, if I think about this regression and I've got delta on the left-hand side, let's say delta is measured well, even if it's not measured well, measurement error in the left-hand side variable, if it's classical, should not bias my estimate of rho. But what if ATE is measured with noise? Then you might expect rho2 to be biased downwards, biased towards 0. And so the Bayesian shrinkage helps a bit to that point because at least the sample noise from the ATE estimates is going down, right? But if there's other types of measurement error that's not purely because sample noise, you may still have that concern.
No, but I guess my question is, don't you want to take into account that you know the standard errors of the ATEs to do something else, to think about that? That's part of your.
Yeah. So I think you might be hinting at, if I know how much measurement error I have in my right-hand side variable, then you can do a measurement error correction under a model of what that measurement error looks like. And you have to make some stances on whether that measurement error is correlated with the other covariates or not, because there's some transmission bias that might be there or not. I don't think they did that, but that might be something that you could do. But you need to have an estimate of that measurement error, and you need to know whether that's independent of the other covariates or not, because there could be some transmission bias. Okay. All right. So let's move to kidney allocation. And so this is a paper that we recently wrote with Paulo and Charles Hodson. And so the idea here is to do both things to some extent, try to estimate measure of the life years effects of various kidney transplantation, various kidney matches, but also then to try and see if we can take these inputs and see whether there's potential for gains in terms of matching people better to help them live longer. Okay. So we're going to say that we're going to evaluate the mechanism on the basis of the kinds of outcomes it produces, which is lift from the current system, whether choice helps or not, and the distributional consequences. So here's the key challenge relative to school seats. Every kidney is different. Okay, so what you've got is that no two people have the same kidney, and so you don't have this situation where you have lots of identical school seats that many students are getting assigned to. Okay, so what we're going to do is, and we're still trying to work out exactly how to say this is different from the rest of the literature, but one thing that's different, and one thing that we're trying to do here is we're going to operationalize this using a characteristic space approach, where we're going to say that kidneys have some characteristics, observed and unobserved, and those characteristics determine the value of the match. Okay, and again, we'll use the randomness in the offers and choice set shifters, just like in the previous paper, in order to make progress. But we'll have a low dimensional choice set shifter. So there was a distance covariate in the previous paper that we discussed, that distance variable that was, there's a distance of each student from every school, which has dimension J, and that helps you identify the system. But now we're going to have a low dimensional choice set shifter. So we'll see how that works out. Okay, so if you did the standard value added approach, which is selection on observables, what you would look at is a graph like this. You would look at young patients versus old patients. This is split on the median age of 53 for kidney patients on the waiting list. And you can see the survival curves of these patients. The red survival curves are the survival curves without a transplantation. The blue curves are with transplantation. The light blue is for high quality donors based on some measure of quality, and the darker blue are for low quality donors. Okay, what you can see is young patients live longer than old patients without a transplant, but also with a transplant. Okay, and the light blue line is for donors who had both of their kidneys transplanted to some patients, and the dark blue line is for donors for whom one of their kidney was transplanted to a patient and the other kidney was not transplanted to any patient. Okay, the left and right kidney are basically the same. So you can see there's a gap between the two blue lines. Okay, so you could get a lift measure, which is what the medical literature did, based on just treating it as selection of observables. But if you look at this paper, this picture, you'd sort of be suspicious. A kidney gets discarded if nobody accepts it. Okay, and so that's a choice that patients make. And there's a gap between the blue and the light blue and the dark blue. So the choices are, maybe the gap is because choices are potentially correlated with the outcomes. So we're going to try to do some selection correction here. So there's an assignment mechanism that we discussed. And so here we're going to have a potential outcome framework that has an outcome for every potential transplant between every patient I and every kidney J. And so you observe the outcome for patient I, the untransplanted outcome if they did not get any assignment, and you observe the transplanted outcome if they being assigned to J if they were assigned to J. Okay. Now in our setting, these are censored because we have 15 years of data, but thankfully these patients sometimes live longer than that. Okay, so here's how the system works. And so there's a dynamic assignment mechanism that I told you. So imagine that you are patient I and you received an offer for kidney 1. And you said no. You wait around, you get maybe the offer for kidney 2 and you say no. Then you go to, then you get the third offer, DI3, you say yes, you get a transplant. Okay. And there was a fourth potential offer that, could have happened, but we never saw it. Okay, so that's the kind of data generating process that we're looking at. So we're going to have a characteristic space approach in which yi0 is a function of your characteristics, observed characteristics xi, and your unobserved characteristic nu i0. Okay, Greek stuff is not stuff you don't see. Roman stuff is stuff you see. Okay, well, Yij you don't see always. So then Yij is your transplanted outcome if you got kidney J. That's G1 of Qj, which is say a vector of characteristics, a type of kidney J. In the paper, we have some unobserved characteristics as well, and we're extending it to that case for the identification results as well. The same Xi's, and nu I1, which is your unobserved type if you get a transplant. And then there's epsilon ij1. So we're going to allow nu I1 and nu I0 to be correlated. Okay. This is a survival model, so there's no time, there's no unobserved time evolving frailty. So that's an important assumption here. It's not that over time your unobserved frailty is evolving. Okay, we can have time effects in these x's, but not through the unobserved terms. And there's some deep reasons in survival models why that's kind of a hard thing to identify. Okay. So as in the paper that you saw earlier today, agents are offered objects sequentially, and they must accept or reject. And so there's a decision Dij, which consists of the characteristics of the organ, characteristics of the patient. There's this term Zi, which is going to be my shifter that is going to be used for selection correction. So this is going to be the scarcity of kidneys in the area that you're set up, that you registered. So imagine, we had an optimal stopping problem. Instead of kidneys, instead of bus engines, we were replacing kidneys. And so if you are in an area with a scarce supply of kidneys, your future valuation of weighting is lower. And so you'll have a lower threshold of acceptance. Okay. And so Zi is going to be a one-dimensional shifter, as opposed to a high-dimensional shifter that's going to change the selection threshold. Then I've got nu ID, which is a unobserved selectivity of the agent, and then an epsilon IJD. So selection in this model is going to happen because the nus are correlated with each other. All of the nus are correlated with each other, and the epsilon IJs are correlated with each other. Okay, so there could be selection on match-specific gains. There could be selection on other failure. So you can write down this discrete choice model using the optimal stopping problem. You've already seen that, so I'm going to move on. Okay, so we'll allow for correlations between all the nus and the two epsilons that results in selection into treatment on the baseline outcome. So it could be that people who are sicker or not are more or less likely to be transplanted to any kidney on baseline. On average treatment outcomes, which is people who benefit from any kidney are more or less likely to be transplanted. This is very similar to the school case, where people who may not benefit from, say, the charter schools are more or less likely to be assigned to one or not. Okay, and then match-specific outcomes. And there'll be selection because of the mechanism of the choices and the observables as well as the unobservables. So again, we're going to use two sources of variation. Okay. The first source of variation is the conditional independence of offers in the system. So think of all the potential offers that a patient would have gotten had they said no to every kidney. That set is Ji. Okay. This set depends on what everybody else in the game is doing. Okay. I'm going to say that the unobservables nu I and epsilon ij are independent of those offers, conditional on xi, which is fine-grained control of everything that affects the priority of the patient. Okay. So the randomness is coming from when the kidneys arrive into the system, what the other patients are doing in the system, but not related to, and that generates variation in Ji, and my own nus and epsilons are not affecting it. Okay, so if your unobservables and my unobservables are unrelated to each other, then that's satisfied. Okay, and knowing the mechanism again helps you work out what is the right set of controls xi. So everything that affects your priority is going to be a control. The second thing is going to be that this shifter Zi will be excluded from my outcomes. So I'll assume that the scarcity of kidneys in your particular region is not related to your potential outcomes. So that affects whether you say yes or no to a kidney, but not what would have happened had you gotten this specific kidney. It affects whether you say yes or no to it, but what would have happened to you in terms of life years had you said yes to that kidney. Okay. So this is a low dimensional instrument relative to the distance instrument. Okay. Okay, so let me speed up a bit.
Just one question, you got a question online. Does this method allow for treatment effect heterogeneity on individual covariates, for example, gender?
Technically, yeah. So what I did not tell you, these functions Yij depend on the characteristics of the donor as well as the characteristics of the patient. Okay, so if you include interactions in your empirical specification, it is, but I don't believe we put gender in. We put gender in on Xi, but we didn't interact it with.
Okay.
We didn't interact it with. Kidney care.
Another question, that the XI is general patient characteristics, or is it the patient characteristics that determine whether you're getting?
So it is sufficient to control for your priority types, all the priority types. That's it.
So that XI is different than the previous slide XI.
It can be lower dimensional than that. Yeah.
Is it in general like the allocation mechanism? Is it a high dimensional thing?
It's a lower dimension than all the characteristics. So for example, whether you're pediatric or not matters, whether you're hard to match matters, your blood types matter.
Fully stratify that.
You could stratify on that in principle. Yeah, but we have to make some further assumptions on linearity, like kind of sort of the dummies for these types that enter linearly as opposed to the conditional one. But yeah, in principle, you could do that if it's sufficiently low.
What's the dimension of the epsilon? So these, are they scalar or vectors?
Yeah, so all the nus and the epsilons are scalars.
Okay, so there's sort of limited kind of unobserved heterogeneity.
That is limited to unobserved. So we're putting in this in characteristic space. That's what I mean. Like there's a finite dimension of characteristics that determine these outcomes.
Right, without separate coefficients on the observed.
Well, yeah, we could in the identification results, we require there's some monotonicity restrictions on that, and that's it. The empirical specification makes a few more assumptions, but in the non-parametric identification results in the paper, we don't assume separability.
You could interpret the question as being about that. So why are you computing effect heterogeneity on individual covariates? It's kind of like a separate unobserved term for every covariate.
Yeah. So on observables, we can allow for interactions, and on observables, we're going to have to make a lower dimensional assumption for the non-parametric identification results. And then there's the empirical implementation that is a little bit different. Okay. So in the interest of time, I'm going to skip over some of this stuff. I just want to sort of say that the variation offers has detectable first stage, and the choice shifter has detectable first stage, which is that it is true that people who are in more scarce areas, conditional on location, time period, fixed effects, are more likely to, are less likely to, people in more scarce areas are more likely to accept a given kidney offer. Okay. So let me tell you a little bit about how this, what's the identification challenge here because of the dynamic nature of the assignment and how we make progress. So because we have a non-separable model in principle, what you've got is you can normalize the density of this new D term, which affects your selectivity to be uniform. Okay. So before I see you, the density of nu D is this uniform distribution. Now let's look at people who took their who were given an offer and they accepted their first offer. Okay. Those who accepted their first offer are likely to be less selective than those who did not, right? So what you get is the residual density after those who have selected the offer, the residual mass, not the density really, because I'm not normalizing it to one, is given by this pink line, okay? And so if I have an offer instrument, similar to the one that Parag looked at, what I get from looking at people who got one offer versus none is the treatment effect, conditional on all the other covariates, for people who accept the first offer. Okay. So how do I get that? Well, I observe the outcome for those who accepted the first offer and were transplanted it, and I observe the outcome untransplanted outcome for those who did not. Similarly, I can do that for the second offer and I get a different treatment effect, and third offer and so on. I can stitch these together to get certain types of combinations of treatment effects. But I don't get what would have happened if I give you a different kidney. Okay, because for that, I need to condition on no D. Okay. What the choice set shifter instrument does, the ZI instrument, is that it changes the complier population. So you go from this pink line at a value of Z to this dashed line at a value of Z prime. Okay. Now, there are steps that I'm going to gloss over, but what we do in the paper is to show that with this minimal structure, this characteristic space structure, and this low dimensional Z, we can deconvolve the treatment effects and get it conditional on each of the nodes. Okay, and so that requires some heavy lifting, but I'm going to point you to the paper. So the point is that the scarcity instrument allows you to do this deconvolution. Okay, so it allows you to disambiguate the effect of the match specific term and the no D term. When we estimate the model, we're going to take a similar parametric approach, more parametric approach like in the previous paper, where we will say that there is a joint distribution between the decision equations and the outcome equations. We're going to make them multivariate normal, very flexible covariance terms. And then we're going to take the Box-Cox transformation of this and use a Gibbs sampler to deal with the selection correction and also to deal with the censoring problem. We've got a censoring issue because we see the survival of agents only up to at most 15 years. Okay, so a Gibbs sampler turns out to be quite a convenient way of estimating these kinds of selection models. It's been previously used for correcting hospital selection by I think it was Gauri Sankar and Town. Okay, so that was to get hospital quality estimates, and so that's where this is motivated. Okay, so it has it's a slightly different functional form, but in principle very similar to the one that Parag and Attila's paper did. Okay, and so what that gives you is some estimates of the value of transplantation to various types of patients in terms of life years. And in this graph, what I'm showing you is the untransplanted survival for various patients and the average transplanted survival for those patients. It's a density plot. Darker regions means areas that have higher density. The dots are bin scatter plots from this density. The dashed line is a 45-degree line. And this already gives you some interesting insights. So first, there's heterogeneity in average transplanted survival and life years from transplantation. The slope is positive. So healthier patients on baseline, people who have high untransplanted survival also have high transplanted survival. Okay, and the dots are increasing with a slope that's bigger than 1. So these patients who have high untransplanted survival are also the ones who will benefit more from transplants. Okay, and what I haven't shown you in that picture is also that your probability of accepting an offer is positively correlated with the survival probability. Okay, so as opposed to the previous paper, what we find is that your choices are correlated with high lift, and that might be because potentially doctors know a little bit more about what works well for a patient as compared to maybe what parents know about what's a good school. And then what we can do is we can think about the assignments of various types of assignments, including a theoretical optimal. So the realized assignments results in 8.78 years of extra life years from a patient. Compared to that, the random assignment is at 7.87 years, so considerably lower. The mechanism is doing something in getting people to good assignments. But it's not only the mechanism rule, it is also choice. Because if you just took the priorities in the mechanism and you transplanted counterfactually each patient with the first kidney that they are offered, then that would give you 8 years, 8.01 years. So this gap is coming because of choice. Okay. And then you can see what the optimal assignment, if you were an oracle and knew exactly when every patient's going to die, what that would look like. That would result in many more years. And then there are some other, this is unachievable for sure. And then you can look at other things like Pareto efficiency, constraint that those who are transplanted are remain transplanted, and that changes, that significantly reduces those estimates. So choice seems to be doing something here. But the one thing that we get out of this, one important thing that we get out of this is the planner's dilemma. So as I told you, that the patients who are likely to live long without a transplant are exactly the ones who get the highest lift. So if you transplanted patients to maximize lift, what you would end up getting is you would leave the sickest untransplanted. And society might have a moral imperative against that. And so there's this trade-off that that the planner has to make between transplanting the sickest versus maximizing life years. Coming back to the theme of multiple objectives in market design research. So I'm just going to conclude by giving you a somewhat broader view of thinking about how I at least think about sort of the market design objective and where theory and empirics come in. So market designers do sort of three things in my view. First, they try to diagnose market failures. These could be standard market failures that you're familiar with, like market power collusion, rent-seeking participation, etc. Strategic misreporting that can result in information being not properly revealed, market fragmentation, etc. They also engage themselves in evaluating and comparing designs either from a theoretical perspective or from an empirical perspective. We've seen examples of that already. And we saw some subset of examples, school choice design, organ allocation, public housing, but there are a number of others like allocation of natural resources, course allocation. Sam is going to talk to us during the conference about food banks. And so he has a nice paper that compares the two designs estimating the welfare effects of this pioneering change that Prendergast reports on. And then propose new designs, either using theoretical approaches to justify something or to say that, okay, these new designs from an empirical perspective seem to be good. You'll see an example of that. Pete Kyle is going to come and talk to us about a new design for financial exchanges in the conference. And so that's another thing that market designers do. So these are sort of the three kinds of things that you do. Not one paper doesn't do all of them, right? But papers do many different things. And just to echo what Paulo said, so the goal of the designer is to analyze these rules and develop new ones. Roth and Klemperer have made this point before. A priori, it may not be clear which rules are important. And so one of the jobs is to try to figure out which rules are important and which ones are not. And in this endeavor, it's theory, data, and practice come together really well. As Parag said, theory and data and empirical work have been very closely linked in this space. Theory can help us identify new issues. Data can help us quantify trade-offs, test various hypotheses, and practice allows us to bring new data into bear to our questions and to uncover new designs and understand how the world works in these dimensions. Thank you. That's it. Really appreciate you sort of engaging in this work and thinking about how to make our marketplaces better.